All right, let's talk about the Moivres theorem. So this is what all of the discussion of complex numbers has been leading up to. In your college algebra class, Math 35, you talked a lot about solving polynomial equations. And you talked about a lot of tools for that, I would assume. You probably talked about synthetic division and the rational roots theorem and, boundedness theorems and stuff to find zeros of polynomials or roots of polynomial equations, Anyway, however, there is one tool that belongs in your toolkit that you did not learn about in Math 35, and that is de Moivres theorem, or actually it's kind of a corollary to de Moivres theorem. And this is really cool. It ties together so many things in algebra. So this is one of my favorite things. And of course, trig plays a crucial role in this. So it really kind of unifies all of that, all of the trig and algebra that you've learned. So so here's de Moivres theorem. Let's not gild the lily any further. Okay, so de Moivres theorem, and it says r cis theta. So you've got a complex number written in polar form. If you raise that to the nth power, that's the same thing as raising r to the nth power and then looking at n times theta. Okay, so it's a pretty simple statement, and it's easy to prove because we've actually done all the hard work as far as proofs are concerned. So this is really easy to prove. So r cis theta to the nth power, just by definition of exponents, right? This is r cis theta times r cis theta times r cis theta, right? You're multiplying it by itself n times. Okay, well, this is just, you can collect all of the moduli, right? You just call it r times r times r times r n times cis theta plus theta and so forth n times. And how do we know that that's true? Well, we know that that's true because of the product rule that we talked about in 8.3. Okay, so we know that this is true, and that's where our result comes from, right? R multiplied by itself n times is just r to the nth power. Theta added to itself n times is just n times theta, and that's that. Okay. So, for example, let's say that we wanted to know what. So let's evaluate something like root 2 over 2 minus root 2 over 2i to the 8th power. So let's say we wanted to know what this is to the 8th power. Now we could work with this in rectangular form, the way that it's written now, and we could write this out 8 times and then foil and foil and foil and foil a bunch of times, right? We'd have to do what? 4 foilings, and then we'd have to do like 2, you wouldn't even call them foils because you'd have these, well, I guess they would still be complex numbers. So you'd still do 2 more foils and then 1 more foil after that. So it would take you 7 foilings, I think, to work this thing out. Not very fun, okay? It would take a long time. So another way to do this is to change this into polar form and then use de Moivres theorem and then change it back into rectangular form. So let's do that, all right? To change this into polar form, well, actually, let me do this. Give the video a pause, all right? See if you can do that on your own. But I think that's the best strategy, right? Change it to polar form, use de Moivres theorem, and then change it back into rectangular form. So go ahead and give the video a pause, see if you can do that. Okay, and now I'll work out my solution. So, so changing this guy to polar form, first of all, we need to figure out what the modulus is, right? So we need to figure out what r is. Remember, r is the square root of x squared plus y squared. That's the square root of, well, root 2 over 2, that would be 2/4, which is 1/2, right? 1/2 plus 1/2. Oh, that's nice. This is the square root of 1, which is 1. So r is 1. And then we need to figure out what theta is. And so let's remind ourselves that tangent theta satisfies y over x. So it's got to be negative root 2 over 2 over root 2 over 2. That's negative 1. So theta is not going to be tangent inverse of negative 1 because tangent inverse of negative 1 would be negative 45 degrees. And we want theta to be between 0 and 360. So, so actually what we'll do is we'll let theta be in quadrant 2. So it's still going to have a reference angle of 45 degrees, but we want it to be in quadrant 2 instead of being in negative quadrant 4, I guess you could say. Well, no, hold on a second. I'm getting ahead of myself. Maybe we don't want to be in quadrant 2. We've got to draw a picture to see where we want to be. We want to be in, so root 2 over 2, negative, we want to be in quadrant 4, don't we? We want to be in quadrant 4. Look at me almost leading you astray. But yeah, we want theta to be in quadrant 4. We just don't want it to be negative 45 degrees. We want it to be whatever this positive angle is. So that would be, 360 minus 45, so 315 degrees, right? So theta is going to be 315 degrees. Man, I almost led you astray talking about quadrant 2 and stuff. No, it's got to be in quadrant 4 for sure. Okay, so 315. Okay, well, so that gives us our polar form. So we can say root 2 over 2 minus root 2 over 2i to the 8th power is really the same thing as 1 cis 315 degrees to the 8th power. Okay, because this is the polar form of that number. Now this part is easy, right? This is going to be 1 to the 8th power cis 8 times 315. Okay, so that's going to be 1 cis, whatever 8 times 315 is. 8 times 315 is 2,520 degrees, which is a huge angle. Now the good news is that you can just use your calculator to figure out what cosine and sine of that angle are. If you wanted to, you could try to find a coterminal angle between 0 and 360. With this angle right here, we would just keep subtracting 360, right? So we've got 2520 minus 360 minus 360. I'm going to keep doing that. Oh, no way. Is this really coterminal with 360? Oh, what a boring example. This is 1 cis 0 degrees. How boring. Wow. Okay. Right. But this number turns out to be coterminal with that one. Anyway, so going back to rectangular form now. So we'd call this 1 cosine 0 degrees, 1 times cosine 0 degrees plus I times sine 0 degrees. 1 times cosine 0 degrees is 1. Sine of 0 degrees is 0. So this is just 1. All of that work to get 1 as your answer, you got to be kidding me. But imagine how pissed off you'd be if you actually had to do this in rectangular form and do all of that foiling just to get 1 in the end. And not only that, you'd be almost certain to go wrong somewhere. Anyway, if you have a nice enough calculator, you might be able to do this in your calculator. I think I can. So I'm just going to check my answer here. I'm going to say root 2 over 2 minus root 2 over 2 times I. Where's my I? But right there. I. And I'm gonna. Oh, I got that going the wrong way. Hold on. and then I'm going to raise that to the 8th power. And sure enough, right? So it is 1, which is which is pretty interesting. So so there you go. All right, so there's that one. So that's kind of nice. You know, you may wonder, yeah, but like, who cares? I mean, it's nice, but is it all that useful? And the answer is, de Moivres theorem itself. Now I could be wrong about this, but personally, I don't think de Moivres theorem itself is all that particularly useful. It's the corollary to de Moivres theorem that we're about to talk about that's really useful. The corollary to de Moivres theorem has to do with the roots of numbers. Okay, for example, since this number raised to the 8th power is 1, that means one of the 8th roots of 1 is this number right here. Right? So this is one of the 8th roots of 1. So you may think, well, how could that be? The only 8th root of 1 is 1 itself, because only 1 times 1 multiplied by itself 8 times would give you 1. But you see now that that's not true, because this number multiplied by itself 8 times is also 1. See, strange things happen when you start to throw complex numbers into the mix. But strange things, but nice things, okay? And one of the nice things is that every number, every complex number, has exactly n nth roots. Okay, so every complex number has exactly n nth roots, n distinct nth roots. So 1, if you're looking at the 8th roots of 1, it should have 8. There should be 8 of these things that, when multiplied by themselves 8 times, would give you 1. 8 distinct roots of 1. So, and that's part of the statement of that corollary. So I'm going to write it down. Let's get to the corollary now. By the way, I keep using this word, corollary. Now, I'm not sure if everyone would agree with, if every mathematician would agree with me about this, but when I think of the word corollary, I think it's something that sort of follows from a previous result, from a previous fact. It's, you know, something that follows more or less directly from a previous fact. Anyway, in this case, this is a corollary. I'm calling it a corollary to de Moivres theorem, because it sort of follows directly from de Moivres theorem in the way that we just talked about. If this number to the 8th power is 1, then that means one of the 8th roots of 1 is this number. Okay, so this is sort of a corollary to de Moivres theorem. And so here's what it says. Here's what the corollary says. It says R cis theta has exactly n distinct nth roots, which can be found with the formula. So not only do they have n formula, not only do they have n distinct nth roots, but we're going to tell you how to find them. Here's how to find the n distinct nth roots of any complex number. Okay, so the nth root, you're looking at the nth root of, well, maybe I shouldn't write it down this way. This is not very good. This is not very good notation, because when I write down the nth root of r cis theta, that's only referring to one of the roots. Okay, that's talking about the principal nth root, which actually we don't really have like a great formula for, or a great definition for, I guess I should say. We talk about principal square roots, but principal nth roots in general is a little bit more difficult to nail down. So maybe I'm not going to use that notation, but what I will say is that the nth roots can be found this way. So the nth roots of r cis theta are going to be nth root of r cis theta plus 360 degrees times k over n, where k can be 0, 1, 2, 3, 4, and so forth, all the way up to n minus 1. That's the formula. It's a little confusing at first. Pause the video so you can write it down, you know, but I'm going to explain to you some key things. So first of all, we're looking at the nth roots of this number. So n here and n here should match. If we're talking about the eighth roots, for example, if we wanted to know the eighth roots of 1, then we would look at the eighth root and the 8, and that denominator would be 8, right? And 8, we would stop here at 7. We would stop. So k could be any number between 0 and 7, right? And if you count up those numbers, that gives you 8 roots, right? 0, 1, 2, 3, 4, 5, 6, 7 is 8 numbers in total, okay? So that gives you 8. It gives you all 8 of the 8th roots, okay? So more generally speaking, right? This formula gives you all n of the nth roots of any complex number, right? You just have to write it in polar form first, okay? So let me give you an example of this. So let's find all 4th roots of -8 plus 8i root 3. So we want the 4th roots of this number. So we're not trying to raise this to the 4th power. We're trying to find the 4th roots. We're trying to find what numbers multiplied by themselves 4 times would give us -8 plus 8i root 3. Now you can do your best to try to figure that out just by guess and check, but you would probably be here literally forever trying to figure it out by guess and check. So a much better thing to do would be to apply this corollary to the Moivres theorem that we just talked about. So go ahead and give the video a pause and see if you can do that. Obviously, your first step is going to be to change this number into polar form. So write this number in polar form, then see if you can apply de Moivres theorem, or the corollary to de Moivres theorem, to find the 4th roots of this number. So give the video a pause, see if you can do that. Here's my solution. So I'm not going to make the same mistake I did the first time. Let's draw a picture of the complex number so that I know what quadrant theta is supposed to be in. So -8 plus 8 root 3 I. So we should be in quadrant 2, okay? So our modulus, R, is going to be the square root of -8 squared plus 8 root 3 squared. That's going to be the square root of 64 plus 64 times 3. So really, I guess it's just 64 times 4. So the square root of, oh, maybe I should do, hold on. 64 times 3 is 192. And then 192 plus 64 is 256. And I feel like that's got to be a nice answer. I think that's 16 square root of 256. Is that right? Yeah, 16. So R is 16. That's nice, right? That's very nice. So R is 16. And then tangent theta is y over x. Well, that's just negative root 3. Okay. So theta is not going to be tangent inverse of negative root 3. Because tangent inverse of negative root 3 would be here in quadrant 4. It would be in negative quadrant 4. But what we can do is add 360 to get us into quadrant 2. So I'm going to say this is tangent inverse of negative root 3 plus 360. So that we end up in the correct quadrant. We could do that one in our heads, right? Negative root 3. I'm too lazy though. And that's negative 60 degrees. So plus 3, so this is going to be not 360, 180. I'm sorry. Man, how am I doing today? It must be a Monday. It must be early on a Monday. Anyway, so plus 180, sorry. If you add 360, you end up in quadrant 4, but I want to end up in quadrant 2, so I'm going to add 180. So that puts us at 120 degrees. Okay. Okay, so really the complex number we're talking about here is going to be 16 cis 120. Okay. We want the 4th roots of that guy. So applying de Moivres theorem, right? Here's what de Moivres theorem says. It's going to say the 4th roots are going to be Well, first of all, 4th root of 16, cis, theta, right, 120 degrees, plus 360 degrees times k, divided by 4, where k can go from 0 to 3, right? Since n is 4, we stop at 3. Okay, so those are my 4th roots. So what I'm going to do now to generate my this rule generates my 4th roots. And now to actually see what they are, I'm going to take turns plugging in numbers for k, right? 0, and then 1, and then 2, and then 3, to see what I get. So for k equals 0, I get, well, 4th root of 16 is 2, right? So I get 2 cis 120 degrees divided by 4. So that's 2 cis 30 degrees. Okay, for k equals 0, or k equals 1, I get 2 cis 120 plus 360. Well, let's see, 120 plus 360 is 480. 480 over 4 is 120. So 2 cis 120 degrees. For k equals 2, I'm going to get 2 cis 120 plus 360 times 2. 360 times 2 is 720, right? So it's going to be 120 plus 720. That's 840 divided by 4. That comes out to 210. 2 cis 210. And then one more. Okay, for k equals 3, we're going to get 2 cis 360 times 3 is 1080. 1080 plus 120 is 1200. So it's 1200 degrees divided by 4. That's 2 cis 300 degrees. What you'll notice is that these angles are equally spaced apart, right? So starting at 30, to get from 30 to 120, you would add 90 degrees, right? To get from 120 to 210, you would add 90 degrees. To get from 210 to 300, you would add 90 degrees, right? And then if you add 90 degrees again, well, you end up right back at 30. Okay, so it's cyclical. But these angles, that's a feature of reality, I guess you could say, right? Is that these roots are equally spaced around the unit circle. Okay, they're equally spaced. That's going to be true regardless of what root you're talking about. So here we're talking about 4th roots, but this would be true if you were talking about 17th roots or any other root you like. Okay. So the roots are going to be equally spaced apart around the unit circle. Okay, now if we want to change these back into rectangular form, we can do that now. I'm not going to write out the expanded forms because I'm running out of room on my page. But just remember, cis means cosine I sine. So we want to figure out cosine 30 degrees and then sine 30 degrees, right? So cosine of 30 degrees. So this is going to be 2 times cosine 30 degrees. Should be root 3 over 2. And sine of 30 degrees should be 1/2. Okay, so go ahead and distribute the 2 and you get root 3 plus I. Okay, so that's one of the 4th roots. That's one of the 4th roots of -8 plus 8I root 3. Okay, next one. 120. 120 has a reference angle of 60 degrees. Cosine of 60 degrees would be 1/2, but we're in quadrant 2 and cosine is negative there, so this is -1/2. Sine of 60 degrees is root 3 over 2, and sine is positive in quadrant 2. Okay. You're welcome to use your calculators too, by the way, if you don't want to have to go through the thought process. At 210 degrees, we'd have a reference angle of 30 degrees again. But we're in quadrant 3 now, so these are both negative. And then at 300, the reference angle would be 60 again. This time we're in quadrant 4, so cosine's positive, sine is negative. Okay, so 1 minus root 3i. And there they are in all their glory. Okay, so those are the fourth roots. Those are the four fourth roots of 16 cis 120. Or I guess the one we started with, right? They're the fourth roots of negative 8 plus 8i root 3. You're welcome to check that, by the way. The way that you would check it is you would raise this number to the fourth power and make sure you get that number, right? Or raise this one to the fourth power and make sure you get that one. Let me just check one of them. So I'm going to do root 3 plus I raised to the fourth power. And sure enough, you get negative 8 plus 8i root 3. I wonder if you go the other way around and raise this thing to the 1/4 power, if you get, well, you just get that first one. You just get that first answer. You don't get any of the others. So it doesn't give you any of the other roots. So you've got to do those by hand. Anyway, maybe in like Mathematica or something, Wolfram Alpha, you know, you might be able to get all of the roots, but that's not going to do you any good if I want to see the work on a test or a quiz, right? I suppose you could use it to check your work, but that's that. So so that's how we find roots of complex numbers. You could do this to find roots of real numbers as well. In fact, I'm going to show you an example of that here in a second. But one thing that I want to mention real quick first is that back in 8.1, when we first started talking about complex numbers, we said that, well, first of all, we defined I to be the square root of negative 1, right? So we defined I to be the square root of negative 1. And then we said, if we throw this new number into the mix, we get the you know, if we add this number into, you know, the real numbers, then now we've got the complex numbers. And once we have the complex numbers, suddenly we get solutions to all polynomial equations. And so it's sort of like the buck stops with this number. There's no need to define any new numbers. And you may think, well, but is that really true? Like, how could that possibly be? For example, you know, if we were looking at something like x squared plus 1 equals 0, this equation doesn't have any solutions among the real numbers, but it does have solutions among the complex numbers, right? You can move the 1 over and then take square roots, and you're going to get plus or minus I. And, you know, we have I, and so we can describe the solution set that way. But what if you had something like x to the fourth plus 1 equals 0? You try the same trick on that. Now you're going to get x equals plus or minus fourth root of negative 1. But what is the fourth root of negative 1? It's not I, right? I times itself 4 times is not going to give you negative 1. I multiplied by itself 4 times is going to give you positive 1. Okay? It's not negative I either. Negative I raised to the fourth power is also going to give you positive 1. So what in the world is the fourth root of negative 1? Do we need to define a new number here? Maybe we call this number j, right? Do we need to do something like that? And for that matter, do we need to do this with all of the even roots of negative numbers? Do we need to define a new number for each of those? And Moivres Theorem is telling you, actually, this is the fundamental theorem of algebra, which hopefully you covered in Math 35. But what the fundamental theorem of algebra tells us is that no, you don't need to do this. All of the solutions to our polynomial equations, such as this one, are contained within the complex numbers. In other words, we can solve this equation just using square root of -1. We don't need fourth root of -1. Another way to phrase the question is, if we know that this number is a complex number, that means that this number has to you have to be able to rewrite this number in the form a plus bi. Well, how do you do that, right? In other words, what is the fourth root of -1? Well, let's check it out, right? So we want the fourth roots of -1. Well, what's -1 in polar form, right? -1 is written in rectangular form this way. In polar form, this would be 1 cis 180 degrees. Okay. You're welcome to pause the video and work that out yourself if you're not sure how I'm coming up with that. But yeah, it should be 1 cis 180 degrees, or in other words, just cis 180. Okay. So that's the polar version of -1, and we can find the fourth roots of this thing. Okay, so the fourth roots are going to be fourth root of 1 cis 180 degrees plus 360 degrees times k divided by 4, where k can go from 0 to 3. So then we take turns plugging in k, right? So we get, when k is 0, we get 1 cis 180 degrees divided by 4, so 45 degrees. I'm going to go ahead and work that out. Cosine 45 is root 2 over 2. Sine of 45 is also root 2 over 2. So this is root 2 over 2 plus root 2 over 2i for k equals 1. 360 plus 180. 360 plus 180 divided by 4 is 135 degrees. Okay, so this is 1 cis 135. Okay, so it's just 90 degrees apart. So this is going to be negative root 2 over 2 plus root 2 over 2i. I think I see where this is going. For k equals 2, we're going to add 90 degrees again. We're going to end up with, what? So plus 90. So we're going to end up with 225. So this is 1 cis 225 degrees. We're in quadrant 3 now, so they're both negative. And then for k equals 3, we're at 315 degrees. Cosine's positive, but sine is negative. Okay? And so there they are, right? Those are the fourth roots of -1. Notice that we don't need to define a new number here, right? We can rewrite the fourth roots of -1 in terms of the square roots of -1. These are the fourth roots of -1. And again, you can prove this, right? You can raise each of these numbers to the fourth power, and you should get -1 as your answer. So I think that's pretty cool, right? It's like the buck stops with the complex numbers. Once you define the number I, there's no need to define any other number. Okay. Once you have the complex numbers, you have everything you need to describe any solution set to any polynomial equation. So it's a pretty cool thing. It's a pretty powerful thing. Okay, moving on. Let me give you another example. We'll do this with cube roots because I want to make a point here. So let's solve x cubed minus 1 equals 0. And I'm going to solve this in two different ways. One of the ways is something that you've been able to do since, Algebra 2 or whatever equivalent of Algebra 2 that you took, or possibly even Algebra 1, honestly. You may have been able to do it in Algebra 1. So that way involves us factoring this as a difference of cubes. So remember the difference of cubes formula and see if you can factor this as a difference of cubes. And then you'll have to use quadratic formula on one of the factors. But you should be able to get all three solutions to this equation. Okay? If you're thinking, well, there's only one solution, it's just one. You're wrong, right? Every complex number has exactly 3 distinct or it has exactly 3 distinct cubed roots. And so if you're thinking, well, I add 1, take the cube root. Well, yeah, but there's going to be 3 answers, 3 distinct answers. Anyway, give the video a pause. See if you can do it by factoring. Okay, so here's my solution. Here's how I would do this by factoring. So x minus 1 is a difference of cubes, like I said. A difference of cubes factors like this. So you have base, base, base squared, base times base, base squared. And the signs are same, opposite, always positive. If that all just sounds like gibberish to you, that's okay. However you learned it is fine. I'm just going to clean it up a little. X squared plus x plus 1 equals 0. Okay, so now I want to solve this. This trinomial isn't going to factor any further. So if I want to solve it, I have to use quadratic formula. This one, this factor gives us the solution that we knew, right? X equals 1. We knew that that would be one of the solutions. Okay, so we can say, well, so x minus 1 equals 0, or x squared plus x plus 1 equals 0. If x minus 1 equals 0, that means x equals 1. If x squared plus x plus 1 equals 0, well, then that means x is negative b plus or minus square root of b squared minus 4 times a times c over 2a. That comes out to negative 1 plus or minus square root of 1 minus 4 is negative 3 over 2. Or in other words, it would be negative 1/2 plus or minus root 3 over 2i. Okay? And there you go. There are the solutions. So there's 1, 2, 3 solutions to that equation. That's how you would solve it by factoring. Okay? Now pause the video again. See if you can solve this using the corollary to the Moivres theorem. Okay? So add the 1 to the other side and then find the cube roots of 1. Okay, so I'll let you work on that. Okay, so now here's my solution. So the other way to do this problem is I would say, well, if x cubed minus 1 is 0, then that means x cubed is 1. And that means that x is a cube root of 1. So I want to find the cube roots of 1. There should be 3 of them. Okay? So the cube roots of 1. First of all, I guess we should say in polar form, 1 would just be 1 cis 0 degrees, or in other words, cis 0 degrees. So it's pretty simple. Okay. Now the cube roots of that are going to be cube root of 1 cis 0 degrees plus 360 degrees times k over 3, where k can be 0, 1, or 2. We stop at 2 because n is 3, right? So we stop at n minus 1. Okay? So for k equals 0, this is going to be 1 cis 0 degrees. For k equals 1, this is going to be 1 cis 360 divided by 3 would be what? 120? 120 degrees. And for k equals 2, this is going to be 1 cis 720 divided by 3. Should be 240, I think. 720 divided by 3 is 240. Yep, 240 for sure. Now, 1 cis 0 degrees is 1. Okay, that corresponds to that solution right there. 1 cis 120. This would be 1 times cosine 120. Well, cosine 120 is going to be root 3 over 2. Is that right? No, cosine 120. We have a reference angle of 60. So cosine's 1/2. Yeah, this is going to be negative 1/2 plus root 3 over 2i, because we're in quadrant 2, sine is positive, cosine is negative. So this is going to be negative 1/2 plus root 3 over 2i. Okay, so that corresponds to the top one, right? We got that solution. 240. 240, well, that also has a reference angle of 60, but this one's in quadrant 3, so both are negative this time. So this is going to be 1 times negative 1/2 minus root 3 over 2i. That's negative 1/2 minus root 3 over 2i. And there you go. There's where you get the negative one. Okay. So that's another way to solve the problem now. And you may wonder, well, so if we already had a way to solve them before, why did we need this new way? And the answer is because we didn't have a way to solve them before. We couldn't have done x to the 4th plus 1 equals 0, for example, because we don't have a way to factor sums of fourths, right? There is no factorization for that. So that's why. Let me give you one last example of this. So let's say that we wanted to solve something like x to the 7th plus 128 equals 0. There's no way to solve that thing by factoring that I'm aware of. I don't know of any kind of, I don't know of any kind of way to factor that. So this is one where you have to use the Moivres theorem to solve this thing. So go ahead and give the video a pause, see if you can do that. Okay, now here's my solution. So if x to the 7th plus 128 equals 0, that means that x to the 7th equals negative 128. So I want the 7th roots of negative 128, right? In fact, I can say that means that x is a 7th root of negative 128. Well, negative 128, what would that be in polar form? This would be 128 cis 180. I'm squeezing it in there, but it's 128 cis 180, okay? So let's see if we can find the 7th roots. Oh, this is going to take some space, isn't it? But the 7th roots are going to be, well, it's going to be the 7th root of 128 cis 180 degrees plus 360 degrees times k divided by 7, where k can start at 0 and end at 6, right? At n minus 1. Okay, so let's see what these are. Let's see if I can squeeze them all in. So for k equals 0, 7th root of 128 should be 2. Right? 2 to the 7th power, yeah, it's 128. So that's 2. So for k equals 0, this is going to be 2 cis 180 divided by 7. Ooh, that is not pretty. So I'm just going to give the exact answer, 180 degrees, excuse me, divided by 7. But here's an approximation now. So cosine of 180 over 7. So this is 2 times 0. Let's go 2 decimal places, so 90. Sine of 180 over 7 is approximately 0.43 I. So you can multiply by 2 now, right? This is 1.8 plus 0.86. Oh, I should have been able to do that in my head, of course. Anyway, but there's one answer. Okay, now we've got to do that 6 more times to get the other 6 answers. I don't know if I'm going to finish the problem because I think you see kind of how this works, but there's going to be 2 cis 180 plus 360. It's 540 divided by 7. Of course, it doesn't go in evenly. All right, so this is going to be 540 over 7. So this is going to be 2 times cosine 540 over 7 0.22 sine 540 over 7. It's about 0.97 I. For k equals 2, it's going to be 2 cis. 360 times 2 is 720 plus 180 is 900. Divided by 7, well, that's just 900 over 7. But let's see. Cosine of 900 over 7 is negative 0.62. And sine of 900 over 7 is, plus 0.78i. Okay, I'm not going to finish the rest. You would keep going until you'd plugged in all the way up until k equals 6. But let me just see. So this would be what? This would be 0.44 plus 0.94. No, 1.94. Sorry, 1.94i. Okay. And then here we get negative 1.24 plus 78 times 2. So 1.56. Anyway, so you'd keep going, but those are the first 3 solutions anyway. So you'd keep going like this to get the other 4, and you'd stop when you stop at k equals 6. So that's that. Okay. So so now you have pretty much all of the tools to solve polynomial equations that are sort of generally widespread known. I'm sure there are other tools out there that we don't cover in, like, college algebra, but they're kind of a specialty, I would say. These are the, when you throw de Moivres theorem into the mix, that's really like that, together with all the stuff you did in Math 35 with the rational roots theorem and all of that. This is really all of the main techniques that we have for solving polynomial equations. So you are well equipped now for solving polynomial equations. But that's it. That's all I'm going to say for that. So I'll see you in the next section.